Welcome everyone to the August 5th OMR Architecture Meeting. Today we have one topic to discuss. So Mark Studley will be presenting his work on JitBuilder 2.0 and its latest state. All right, turn it over to Mark.
Thanks, Cheryl. So this is going to be a fairly impromptu update. I wasn't able to spend as much time preparing slides and material as I had intended, but I do have a few slides just to kind of get going, and then I'll do a bit of a demo for where I am right now. So I guess let me share the slides such as they are. All right. So fresh, this is still presentation 1. All right, so I thought I would start by just kind of giving everybody a bit of a refresher on JitBuilder 2, because it's been a while since I talked about it here, so I just wanted to kind of bring people up to speed on things. This is mostly a refresher of things that existed the last time I talked, but some of it's a little bit new and some of them have slightly different slant, but I'll do my best to go through it. So this first page just kind of goes through the main characteristics of the intermediate language that is JitBuilder 2. That is the main contribution of JitBuilder 2.0 over and above the JitBuilder library that exists in OMR today, is that it basically turns the JitBuilder API into a more fully fledged intermediate language that you can introspect and work with. So in sort of I'll use the term loosely, formalizing the JitBuilder API into an IL. It has sort of these basic parts to it. There are types, as there are in the JitBuilder API. So a bit of primitive types, a thing called a struct type, a union type, and a new thing called function type. So functions become a more first-class citizen of the type system that's in JitBuilder 2. All of those types get stored into a thing called a type dictionary, which kind of sits off on the side. And as you're working to create IL as part of a function, you refer to the types from a particular type dictionary. There are other sort of fairly nice, easy to understand concepts for anyone who's worked in compilers. There's a thing called a literal value, which just holds a constant instance of some kind of a type. So it's a typed thing. There are symbols to represent things like parameters, local variables, and functions. There are operations, which are the names for the calls that you would have made in JitBuilder to cause various things to happen, like load a variable, subtract 2 values to produce a new value, index into an array based on an element size. Do a for loop, or do control flow, like if compare 2 values to see which one, if one's greater than the other. There are values which are consumed and produced by operations, and they are typed, just like most compilers would do. Control flow and organizing things. And organizing the sort of control flow graph, if you will, of a function is done via builders. A builder is basically a label that's followed by operations. It's not quite like a basic block, even though that definition kind of makes it sound like it, because the operations themselves can have internal control flow. Like that for loop operation, for example, represents internal control flow over another builder object that's dictated by the values that you pass to the for loop operation. And then there's a special kind of builder called a function builder, which is essentially a callable entry point that has typed parameters and return values. So these are all very similar to the concepts that were in JitBuilder 1. I've renamed a few of them as functions, not methods, and sort of taken the IL out of most of these names. In JitBuilder, you have IL types and IL values and IL builders. I took the IL out of all of them and just called them builders and values and types. There's also a more formalized notion of a source code location, which you can introduce into your code, which can get passed down into the generated code, so that you can relate the operations in the IL with actual source code locations. There are a number in JitBuilder 2. There are a number of new things compared to JitBuilder the JitBuilder library that allow you to do, this is where you start being able to do some of the more powerful things of a compiler. I would say this is still at a fairly rudimentary level in terms of fundamental features here. There's still no notion of an optimization pass or a sequence of passes, but obviously that's something that should be introduced at some point. I guess let me just go through them. So config is just a collection of useful things right now. It's a set of options and flags and a place to put stuff. That really needs to be formalized a little bit better, given a better life cycle for when the config applies and so on. But right now it's just kind of a place to collect options and configuration things for running a compile. There's a thing called a type graph, which is maintained by the type dictionary, which is used to record legal operation operand type combinations. So basically, this is the mechanism by which JitBuilder 2 verifies that you don't create illegal IL, or at least some aspects of illegal IL. So it will verify, for example, that you don't try to add types that aren't that you can't add together. So you don't add an int 8 to an int 32. You have to convert one of them to the same type and then add those two types. And then the other piece of the type graph is that it dictates what the resulting type will be for an operation. So from the input operand types, it will tell you what the output type is going to be. And then from that, it can propagate all the types through the IL and make sure that when you're generating IL, it tells you when you're making mistakes closer to the point where you're actually making them. Rather than with JitBuilder, you kind of find out somewhere deep in the bowels of the compiler that something's not quite right, and then you have to work backwards. There are a couple of very rudimentary kinds of helper classes that help you traverse IL and do interesting things. There's the visitor pattern, which is pretty much what it says. It basically just gives an extensible class where you can subclass and override, visit operation, for example, and you get callbacks for every operation as it walks through the graph. It ensures that you visit every builder object exactly once and every operation and every builder exactly once. So it takes care of the mechanics of visiting things, basically. And then there's a transformer class that's built on top of that, which allows you to, in addition to being visited or being called for every operation, it allows you to return a builder object that says, replace the operation that I'm visiting with this builder object. And since a builder object is an arbitrary amount of code, you can basically replace any operation with any other combination of other operations. And let's see, and then there are a few implementations of those things in the actual JitBuilder 2 code base. So code generator is the most useful one, the purpose of that one is basically just to generate native code for the IL in a function builder. So it just basically converts all the JitBuilder 2 IL by walking over it and making calls to JitBuilder right now. And obviously JitBuilder itself drives the OMR compiler and creates the native code for a function that can then be compiled. That's a temporary state of affairs right now. It's kind of it was the easiest way to bootstrap JitBuilder 2, but obviously going forward, I think the right way would be for code generator to directly generate the IL for the OMR compiler, or in principle, it could generate the IL for any compiler. Append builder inliner is really the first example of a transformer that I wrote. It's not all that useful, but there is an operation in JitBuilder called append builder, which basically says take this builder and act as if it's in line in the current builder. So if nothing else branches to that builder, like jumps directly to the builder that's in the append builder, then you should be able to actually just inline those code. And so all of this append builder inliner just walks around looking for append builder operations where the builder object isn't called by anything else, and so then it just inlines the builder object directly into the parent builder, the builder that contains the append builder operation. It's not actually used by anything right now. It's just kind of an example. And then there's another thing which I call dialect reducer, which I guess is a bit of a reference to some of the similar kinds of things that are in MLIR. So this is basically a transformer that kind of shows how to replace a for loop operation with lower level operations. So it shows you how to reduce more complicated operations into lower level operations by using this transformer mechanism. So this is basically where I don't think there's anything really new in here compared to what I would have talked about before. And so now, what's different now? I don't have a slide for this. So on Friday, I pushed to the OMR repo a new pull request that's I've marked it as work in progress, but it's the implementation so far at this point of JitBuilder 2.0. It's I guess if you count lines of code and files, it's like 16,000 lines of code or something at this point. So it's a very substantial piece of stuff, which I don't recommend anybody go and review in detail. I don't nitpick on code style or anything like that. I put it there more or less just so that people could take a look at it and see what's in it. I did write a fairly comprehensive pull request comment on it. But let me spend a few minutes now talking about some of the new things that are in that prototype that I haven't talked about before in this meeting. So there are really three kinds of facilities here. I think I have talked about the debugger a little bit on one of my previous talks, but I'll cover it again now because it has changed fairly substantially in the meantime. So the first thing that I'll talk about is actually something that I added since Friday. I pushed this, I think, last night or the night before or something like that, and added it to the pull request. So previously, if you were going to add a new type into JitBuilder or a new operation into JitBuilder, you'd basically have to go in and start editing the class files for operation and type and add the new code in there and then compile it all together. And so if you were going to maintain that as a person trying to maintain a compiler that's built on top of JitBuilder 2, it's a little bit more awkward because you're always kind of folding code in. You'd always have to be folding your code into the existing sort of base classes. And that's a little bit awkward, and it's not really the way I wanted it to work ever, because it makes it hard to write tests for that kind of facility. It gets hard to write a test for a new type being added because I have to actually modify the class in order to add a type and then compile it into JitBuilder 2. So that's kind of an awkward testing story. And I didn't want it to be an awkward testing story. So what I managed to get done this week finally was to add more programmatic sort of ways to add new types. So you don't necessarily have to add a type class, but you can add a new type object that can then be referred to by other things, and it can flow through. You can create values of those types, and operations will naturally be able to work with those values. And you can add new operations in the similar kind of way. You create a thing called an operation builder, which is, you can think of it kind of like the objects of operation builder are each object corresponds to a new kind of operation. So it understands what the shape of that operation is. Like, does it need one operand, two operands? Does it need a literal value? Does it have a type as a parameter? Those kinds of things. And then you can pass the values that you need to those operations. As like if it has two operations, you can set what those two values are, and then call create on the operation builder, and it will create an actual operation that implements that sort of new facility. And you can create new actions and so on to add it into the system. There are a few convenience mechanisms that make it easier to use. So there's like a if you have an operation builder that just takes two values and produces a result, then there's a thing that you can call that looks almost like you just pass two values and it produces a result. So it's a little bit more awkward to use. It's not quite as simple as just saying add of left comma right and you get a value back. That's the result of the add, but it's not too bad, I would say. And the advantage is being able to do this in a more sort of programmatic way rather than having to actually update the classes themselves is actually quite powerful, or I think it will be quite powerful. I'm going to talk a little bit more concretely about this in the demo that I'll do in probably after this slide. I think it's my last slide. All right, so that's the dynamic types and dynamic operations. Then there's a second new thing, which actually it took a long time to piece together because it's actually a fairly complicated thing. is a transformer called type replacer. And basically you create a type replacer and then you can tell it to do one of two things, well, or actually two of two things. You can do all of them at the same time if you want. You can tell it to replace one type with another. So all references to a particular type, you can change it into another type. And that includes transforming literal values, that includes changing operations and so on. And so the use case that I was kind of imagining here was that, what if you had a function builder that you built that's kind of like a template class, so it has like a placeholder type that you want to be able to generate any kind of function builder that operates on a different kind of a type. You could create that method builder, and then when you've got your concrete class that you want to instantiate it for, you can just replace, in this case, the capital T class with the one that you actually want it to be, like an integer or a double or whatnot. I'm not sure how common that use case is going to be, but that's sort of the idea I had in my head when I created it. The second one is an operation called explode, which basically is designed for taking a user type. And actually, one of the things I should have mentioned when I introduced dynamic types is that when you define a dynamic type, because JitBuilder 2 doesn't sort of natively understand what that new type is, part of what you have to describe to it is how to convert that into the native types that JitBuilder 2 understands. And so the notion there is that you define a layout class or a layout struct. It has to be a struct type, and basically that struct type is designed to communicate to JitBuilder what it is that's inside one of these new types that you're generating. And so this explode operation is kind of taking a function builder that refers to some type, some user-defined type, and then modifying it so that it doesn't actually respond to that type, but instead refers to the constituent pieces of that type. So I give the example here, point2d, where it's got an x and a y inside that are two integers. So it goes through your entire function builder, and everywhere it sees a point2d symbol, it would expand it into two integers called x and y, and well, name.x and name.y. And then anywhere that something consumes a point2d, it will actually generate two copies of it, one which operates on the x and one which operates on the y. And by default, it just replicates the operation. So for an add, for example, if you had if you're adding two values of type point2d in this example, that would convert to an add of the two .x's and another add of the .y's, and then it would remember that each one is the result of the part of the result of the point2d that got produced by the add. I didn't say that very well, but hopefully you get the idea. Basically, you get like left.x plus left.y is stored into result.x. Did I say that right? Left.x and right.x get added together and stored into result.x. And then left.y and right.y get added together and put into result.y. And then the type replacer basically remembers all the mappings between the original point2d values and the constituent .x and .y values that get produced as it replaces the operations. Now, that's a very simplistic view of how to do replacement. It doesn't have to be that simple. In fact, there are examples where you don't want it to be that. Multiplication is one place where it kind of gets more complicated. So there's ways of augmenting the type replacer when you're specifying how the dynamic types are supposed to work and how operations are supposed to work that allow you to override what the type replacer will do and specify new functionality. So I'll give you an example later, which has complex, where each complex object has two double values, real and imag, and the multiply, it overrides how multiply works to do the real times real minus image times image, and then also for the imaginary part to do the real times imag and imag times real for the two values. Hopefully that was somewhat clear. I will talk a little bit more about this concretely in a few minutes. And as I say, this one also supports all the dynamic types. In fact, it's built in order to support user types more usefully. And then the final piece, which I think is one of the more interesting parts and was actually fairly complicated to get going and working properly, is the JBDB, the JIT Builder debugger. So this is basically an IL debugger. I think I demoed this briefly at one of my other, the last talk that I gave on this maybe. The idea here is that you have a function builder and you want to debug it without necessarily debugging the native code that it generates, because it's harder. It can be hard to map back from the native code to the JIT Builder calls that you made. And so at this level, you can debug at the IL level and be able to, figure out what the mistakes are when it's making mistakes. The idea here is that rather than compiling, whether you're compiling a function builder and generating a native entry point that you didn't call the native code and it runs, instead you get back a debugged entry point, which looks exactly the same. It's actually a native function, a callable function pointer. That you provide arguments to and you call it, but once it calls, what you're actually calling is a func that then initiates the debugger to run on the IL of the original of the function builder. And then it actually it's a fairly complex system that I don't really have time to describe, and I won't try to do it verbally very much because it is very complicated. I probably it might be interesting to come back and do another talk on that at some point, but the basic idea is that it compiles every operation. It creates a little function that's for single stepping through each particular operation. And the reason it does that is so that you don't have to define a second implementation for what an operation does. The debugger doesn't have to be taught what operations do, even if they're dynamic operations that you've added dynamically to it. You don't have to tell it what the operation does. You've already done that by implementing the code generation function for that operation. Therefore, the debugger can rely on that implementation to do it. And so it creates a bunch of operation debuggers, which get called if you're single stepping, it calls them one at a time, basically. And even those operation debuggers are fairly complicated for things like for loop, because you can be calling out to other builder objects which contain other operations that you might want to single step through. So they're really kind of like little coroutines in a way. It's kind of cool, actually. But I won't go into any more detail on that. I'll just kind of show you how it works as a debugger. So in the debugger, you can print values. You can print the values of values. You can print the values of symbols, even if they're dynamically dynamic types. You don't have to teach the debugger about that. You can single step through the IL. You can set breakpoints based on operation builder or time. So you can break before or after an operation, before or after a builder object, or at a particular time. So as the debugger executes operations, it basically counts a time step. So the number of operations that have executed since it started executing this method. So it uses that as a notion of time. So you can break 5 steps later or something like that. As I say, it supports dynamic types automatically. The code that you have to write in order to implement a dynamic type is parts of it will integrate into the debugger itself, so that it just works. And one interesting benefit of this is that it actually exercises the compiler quite a bit, because it's doing these fairly complex rewriting of the individual operations of the target function builder. So in the course of debugging a matrix multiply operation, which actually is reasonably simple and doesn't require very much code itself, it will actually compile, I think it's 35, maybe 36 different functions, all of which have different kinds of builders and switches, and it dynamically creates a data type to represent the values of what a value can be. Based on the kinds of types that are referenced in the function. So it dynamically creates that data type. It doesn't exist anywhere in the debugger itself. So it's doing some pretty interesting things, I would say. And it's ended up being a fairly good exercising of the debugger. Although I have to say, debugging a debugger that compiles code with 3 different levels of compilers is not something that I would wish on most people. It had some complexity associated with it, but I got better at it after a while. And that's basically a summary of what's new. what I thought I would do now is, let's see, stop sharing that, and maybe I'll try and do this. Let's see if this works. All right. Can everyone see the this bash terminal I have here? All right. So I'm currently in the directory that contains all of the source code for JitBuilder 2. It's a, like I said, it's about 16,000 lines of code right now. Let's see, how do I want to go through this? So why don't I start with a simple, the matrix multiply example. So I've already compiled this, so I'm just gonna run the stuff because nobody likes watching a makefile run. But basically, no, I haven't shown the matrices. So this example takes two 4x4 matrices and with double values and multiplies them together. And it's this, I've set it up so that it generates a debug entry point. So it jumps into the debugger immediately when you call the generated function. So that's what's basically happening here. And for some reason, it didn't show that it was entering the debugger for the first time. That's weird. Okay, first inconsistency. So basically, when you call it, it essentially sets a breakpoint at the beginning of the method and stops, and then asks you what you want to do. So the debugger has, it's loosely based along how GDB works, but it provides a bunch of sort of nice helper things that you can do. For example, if you want to look at the IL for the method that you're talking about, you can just list it, and it will print it out. So let's look at this briefly. Again, this will be mostly a refresher, I think, for people who've seen this before. So I mentioned type dictionary is a thing that's important because it holds kind of all the types that you work with. So this is actually an additional output I added. It probably shouldn't be there, but the type dictionary, basically everything has an identifier that you can use to kind of search through here very easily. It lists the different types, which all have their own identifiers. In this case, it's a size in bits, the actual name of the type, and what kind of a type it is. So if it's a primitive type or pointer types are defined as well. And if it's a pointer type, for example, what the base type of the pointer is, T6. So this is pointer to double, T6 is double, as you'd expect. As you build more and more complicated types like structs and fields and so on are all added into this type dictionary and are all printed out as part of this output. The function builder itself is here. It has a name, matmult. It has its own ID. Function builders all have F as their prefix. So F0 is function builder 0. It uses a type. So D0 was the type dictionary we just looked at. It has a set of parameters, a set of local variables. You can see each one has an underscore and then a T value to see what its type is, just so that you can see it. And those are the types back from the type dictionary here. So parameter P0 is of type T8. T8 is pointer to double. So that's saying that the result matrix is a pointer to double. A is a pointer to double. B is a pointer to double. And N is a T3, which is a 32-bit integer. The local variables are listed along with their names. And then finally, you get into the operations of the function builder. So this is where they're listed here. They show what the name of the function is that they're in, which builder object, which builder ID. So B0 is the same as F0 here because it's a function builder, but it's also a builder. A function builder is a builder. So B0 and F0 are the same thing, and then an operation with an ID to indicate what operation it is. So, and then the operations are, sort of very straightforwardly written. So loading symbol 1. Symbol 1 here is the same as parameter 1, so that's actually miswritten, sorry. So that's loading A, loading parameter A, loading parameter B, loading parameter C. The loads are now off of symbols, not strings, as they were in a previous version of JitBuilder, but it shows the name just as a convenience so that you know what it is. And then the results of them get stored into values. Things that don't produce values, like this for loop up, don't get stored into a value, obviously, but they still consume values that are produced earlier. So the for loop here loops over a symbol called I, which is S5, which you can see here is 5. So this is the outer loop. and then it goes from, you know, const 0 to const n, or to the n value by 1, and the body of the for loop is builder 1 b1. So if you want to find out what's in the body object, then you have to go and look at b1, which sets up the second loop over j. It has a body of b2, which sets up the innermost loop, which loops over k and has a body b3. And then there's the innermost loop, which is doing the loading values from the, it's a little bit hard to parse, I'm not going to go through it, but basically this is doing an array access into the A array, an array access into the B array, loading the values, and then multiplying them together, adding them together with sum, and storing it back into sum. So it's doing the dot product that it does in the inner loop. There are some other kinds of flags and other values can be stored about the builder. So what its parent builder is, whether it's bound to an object or not. I won't go into that in this talk, but that's kind of a key feature, a key characteristic of a builder is whether it's bound to an operation or not. And then whether it's a target of a branch or not. It's kind of another interesting thing that's stored there. So this has showed us what the IL actually is. So then we can kind of single step through this thing, and it will execute an operation, stop before the next one. And once I do that, so I can print out symbols. So let's print out what A is. So A is a pointer to double, and it has this pointer address. So this is the address that would have been passed into the function when we called the function, and that's the address. We can also verify by printing the value of v0. We can see that it has the same value now because we just loaded A into v0, and we can keep going and doing that. You know, over time, we can collect and look at all the other things. We can set a breakpoint to say at time 5, and then we can continue. It will stop at time 5, and it'll execute 3 more things. And now you can see we're at time 5 and we're stopped ahead of this guy, which we can then start going. We can single step into a for loop, so that's S, and then that goes inside the body in this particular case. Well, as long as we're going to execute the body, it'll go into the body. So you can see now we're in B1, which is the body of the for loop. And we can keep executing inside there. We can go inside the second loop. We can keep going. Now we're in the inner loop, that's over K. You can see we're inside B3 here, B3. So let's see. Let's just keep going through here until we get back out to our for loop. Oh, I did next. Oops. Anyway, that was not the example I was trying to do. So let me see if I can repeat that. Let's do it this way. So what I was trying to show here, so that's the K1. So I'm at the for loop K. So before, the last time I did this, I used S to single step inside the for loop. If I do next, it basically executes a whole iteration of for loop. So it single stepped these, but it didn't show me the results inside here. I guess in principle, I didn't really need to, in a real scenario, I probably wouldn't list these executings to show that it's executing all these things. It would just do it like in a real debugger scenario, but I put these here so that it's easier to sort of follow what's actually happening. And so if I keep doing next, I'll execute all the code, and then eventually I'll get to the end. I can continue. And so I should have printed this out first, but this is the 2 arrays that it multiplied together. If you go and multiply them, you'll find that that's the right result, and then it returned, and the code finished. So that's kind of how the debugger works for the map mult that works with double. Now double is a type that actually exists in JitBuilder too, so it's really quite simple to see the code that was used to write that. Let me just CPP. It's not what I wanted to do, but anyway, it's the same thing. So this is kind of the code that I had to write in order to do this code. So you can see here's the and I've done some stylistic stuff here to kind of make it more obvious where the loops are and so on. It's not necessary to do this, but I just did it to make it a little bit more visual. But here's the for loop over I, here's the for loop over j, here's the for loop over k, and this is the inner loop code, which calls off to some things, some helper functions that I wrote to load a 2D. This loads a of I comma k, this loads b of k comma j, right, and remembers the value of that, and then does the multiply add and stores it back into some. So this is kind of, and then stores the result in 2D in the J loop. It stores the sum once the inner product has been, and once the dot product has been produced. So this is the code that I had to write for matrix multiply. So the next thing that I did, this next example that I wanted to sort of to do was to say what happens when I add a complex type. And so remember I mentioned that I didn't have to modify any of the I no longer have to modify any of the underlying classes of the JitBuilder 2 implementation in order to add a new type or to add a new operation. So there's this file here called complex support, which is about 230 lines of code. I'm going to start actually at the end. So this initialize complex support is something that gets called from your main function. If you want to add these things in, you have to pass in what the type dictionary is that you're going to use. So one of the things, as I mentioned, is that you have to create a layout struct to define what the shape of this complex type is going to be. So that's all that this code's doing. It's defining a struct called, this is just a name that I used. It doesn't have to have this form, but I just said it's the complex type and it's its layout, basically using a kind of C++ scoping kind of naming format. It's really just a string, so it doesn't really matter what's even in there. I could call it X if I wanted to. And then it creates the two fields for real and for imaginary and adds them to the struct. It closes the struct off. And then you do dynamic type create and you pass in all of this stuff. Now I haven't shown you all of this stuff, but the result of that is it basically creates a type object, a dynamic type object actually, but that extends type and called complex. And then I've just made complex into a global variable. It doesn't have to be a global variable. That's how I just did it here. Is it can be accessed from anywhere. So anything can refer to complex, and it will be that complex type object. Now, what are some of these other things? So tell it which dictionary this type is supposed to go into. You give it a name, complex, what its size is going to be. So in this case, it's going to be 2 double objects, so it's 128 bits. And then some other interesting things. I mentioned layout here. What's this complex printer thing is just a little piece of code that can print out a value of the complex type. So it's a sort of a special little piece of code that you write to extend. And so you get passed a text writer. Text writer is just like a logging kind of class that makes it easy to print things out. You get passed what the type is, and you get a void star pointer to what the actual the value that's actually there. So the first thing is it asserts that this is definitely the complex type that we got passed, so that we didn't get passed something else. And then it basically just does a reinterpret cast on the pointer p to a complex value, and then prints it out as the real part plus I times the imaginary part. So that's all that was. This complex type exploder is part of the support for type replacer to be able to replace values of type complex with other things. So similarly, it has kind of a defined form signature that it accepts this. So it's going to explode a literal value that you're passed into its constituent pieces. And so I'm not going to go through this in detail, but basically it breaks apart the literal value and creates 2 smaller literal values, one for the real part and one for the imaginary part, and returns that to the type replacer. Similarly, there's another type of thing called a replacer, which is used for, this is how you augment some of the other translation stuff here. So in particular, remember I mentioned multiply is one of the ones that you have to change. If you are trying to multiply 2 complex values, you can't just do, the real part of the result is real left dot real times left dot right. And the imaginary part of the result is right dot imaginary, left dot imaginary times right dot imaginary, right? That's not the right answer. You won't get the right answer if you try to define complex multiplication that way. So this is a function that will get called um, if if an operation has complex types, it will be passed to this thing to first see if there's something it should do beyond what the default implementation does. And so all it's doing is detecting, is it a multiply operation? And if it is, are they both complex values? And if they are, then it does the cross multiply that I talked about earlier. Everyone knows how multiplication is defined for complex numbers. And so it manages to, it's given a builder object, and it just places the results into that builder object and then does some other things to help with the mapping. And then finally, there's a thing called a registrar, which is used in conjunction with the type graph to basically say what kinds of operations are valid with this class. And so this gives you a callback from the type graph, and it gives you the actual type graph that you can use to register valid operation combinations. So you can say add of a complex and a complex gives you a complex, add of a complex and a double gives you a complex, etc. And so these are all combinations of types that JitBuilder doesn't know about itself because it doesn't know about complex itself, but now it knows that these combinations are legal. And so if it sees a mul with a left operand that's a complex and a right operand that's a double, it knows that that's a valid operation, and it will produce a value of complex type. And you can add all kinds of things. I put in there's some other things that I could have put in, but they're not really supported right now. So it's like there are all kinds of other stuff that you can put in here. And that's basically that for the type. And then I also defined a couple of new operations. So the first one is to insert a const complex operation. Now this probably could have been folded. Now that I have literal values in the IL, I could probably just have a const IL function which accepts a complex literal value, but I didn't do it that way right now. So this const complex builder is, you create, like I said, you create an operation builder. You use this new action thing. Basically, JitBuilder 2 will assign it a new value to correspond to this kind of operation and give it a name, const complex. So when it gets printed out, this is the name that will get printed out in the IL. And then you kind of describe what the shape of this builder object is, and it's kind of a fluent API here. So, it's got one result. The result type is complex. It has one literal it takes one literal as a kind of a literal operand. And then similarly to how the dynamic type stuff had some of these other like complex printer, exploder, replacer, there's a printer for operations, and there's a kind of an expander thing which helps with the how do you replace a const complex operation if the complex type is being exploded. That's basically what it's for. And so this is just a piece of code that takes it just converts the const complex into two const doubles and maps the results appropriately. I also defined another operation which I didn't actually even use anywhere, but just to show that it could be done. A different example of doing it, so like a conjugate operation. So another sort of complexy kind of operation. So it's got one result, which is going to be of type complex. It has one operand, that means a value that it would take, and it has an expander and a printer, and this one also has a registrar. So this registrar is basically saying that there are some combinations of operands that need to be tested here. And so in this case, you can see it registers a valid operation for this conjugate builder, which I have to get its action from it, and then it takes an operand of type complex and produces a result of type complex. And then that's basically it. That's what you have to do to add one new type and two new operations into the world. And so with just this code, just this 230 lines of code, type replacer, code generator, and debugger all know exactly what to do. So without modifying debugger, I can I can debug it. So, well, at least if I run the right thing. All right. Or maybe I can't. That's unfortunate. That's gonna blow my demo. All right, shoot, I must have changed something last night that I didn't anticipate. All right, this used to work, but at least it's gonna show you what the code is that's being generated here. So honestly, this is almost exactly the same code, but the type dictionary has so I've given it a new name. So you can see there's a few new things here in the type dictionary compared to what we had before. The complex layout type has been added, right? The one that we created in that initialized complex support, right? So it's a struct type, which has two fields, which are dictated by T10 and T11, that the various ones that offset 0, the others that offset 64, so 8 bytes in. T10 is the real part, which has a field type of T6, which is a double. And then T11 is the imaginary part, offset 64. The actual dynamic type that we defined is this guy here, T12. So you can see there's this complex, it's a primitive type, and it has a layout class that's been identified as T8. So that's that complex struct type that we talked there. And then it also, for free, we got a pointer to complex type that we're used here as well. And so in terms of what the function builder, what changed in the function builder when we were doing this is now the parameters to the function had to change, because now you're taking pointers to complex arrays, not pointers to double arrays. So we're using that T13 type, the pointer to complex. The values like sum are now of type T12. So the T12 is the complex primitive type. So T12 itself doesn't know about real and imaginary parts. It's just a type that says I'm complex. You have to look at the layout type to find out what the pieces are. You can see here the only other change that was needed in this whole code, other than sort of updating the type references to use complex instead of double, is to change the initialization of the sum variable that's used for the dot product in the inner loop. Is now starts off as a const complex value, which gets printed by our little printer, and uses the name of the operation that we specified. And other than that, the code is identical. It just works with values, uses the original JitBuilder calls. It's quite convenient. That's kind of annoying that happened. And it's reproducible too, so I won't be able to show you, unfortunately, the debugger experience. But basically, once I fix this problem, the debugger will just work. It simply uses all of the definitions that were provided to generate code and to do the type replacement. And the way the debugger operates, it basically queries every opcode, and dynamic operations can answer those queries just as well as built-in operations can. And the type replacer automatically causes the complex type to be exploded into two doubles wherever it gets used, and it converts all of the different operations appropriately to create all of the operators. And so you can single step through that code. I wish I could show it to you. You can print a symbol that has a complex type, and it will print as that comp type. It'll do the same, real part plus imaginary times the imaginary part. If you print values, that they'll do the same thing. Single stepping, all of that stuff just kind of works out of the box. So until I ran into this assertion, I thought everything was working quite handily with that. So, okay, so now, so that's the end of the sort of demo, ending with an assertion. Now, I guess, so where am I going? Where do things go from here? So I have created the pull request. Obviously, it needs to be updated, so please don't merge it until I fix this assertion. What I'm hoping to do is or I guess what I'd like to propose to do, I'd like feedback on this. I'm thinking to create a project at the GitHub, at our GitHub repo for this, for the JIT Builder to work, and then start tracking all of the different things that would need to be done in order to get it both integrated into the code base as well as begin to get worked on by me or whoever else wants to help out with this. There are a number of areas that that need improvement right now. So there's some things. It's definitely a prototype right now. This is not something that I would recommend. Should be used aggressively by anyone. Even though it does have some fairly good and fairly broad functions right now. I've been trying actually to keep the API surface area fairly small so that I could still change some things fairly easily. But what I needed to do in order to implement the debugger kind of caused that surface area to grow quite a bit. Let's see. Some of the things that I would like to fix about it, but don't necessarily have to be done right away. So I guess, maybe I should focus on things that should be done right away. So right now, the JIT Builder 2 implementation is completely unintegrated into OMR. It's sitting in a directory underneath the JIT Builder directory right now, called JBuilder. It has a little small makefile in it that assumes that you've built the JIT Builder library somewhere else. I've only ever run it on Mac OS. But there isn't very much about it that's Mac OS specific. You just need to point it at where your build directory is, and it will go and find the libJIT builder that's there, and it will link together with the libJIT builder 2 files. There are a number of little code samples in there. They're very poorly named, but they do things that exemplify how it works. There is the complex support case, which doesn't quite work with the debugger yet. Let's see. So I think if we're going to add this into the OMR project, I think it would be good to at least have it integrated into the CMake build system. So that's one thing that should probably be done, either before or as a first priority once it's merged. As I said, it's about 16,000 lines of code right now. So while I don't want to use that as an excuse, at some level, if we're going to go through and try to fix everything in that 16,000 lines of code, it's going to be a long time before it gets absorbed into the code base, and a long time before anybody can help me or help work on it, basically. So I would welcome people's thoughts on how you would prefer to integrate this. I know it is a big pull request, and I'm generally not a fan of big pull requests. So I'm a little bit conflicted about this one, I have to say. But I do kind of want to get this into the code base and accessible to people, and if anybody wants to help, I would very much welcome help with that. And maybe I'll just stop there, basically, since I've been talking for almost an hour now, and see if people have thoughts on the integration question. Sounds like no. Can anyone hear me?
Yeah. No, that was very interesting, Mark. Yeah, I don't have any specific thoughts on the integration aspect of it. I mean, what you propose seems reasonable to me. Certainly like the idea about creating a project to track the different pieces of work that need to get done as well. In fact, we should probably maybe even be doing a little bit more of that at the OMR project for other things.
Yeah, so I mean, one of the areas that I really want to put some focus on before trying to expand the implementation very much further is to put more of a stronger emphasis on writing tests for it. That's kind of a trap that we've allowed ourselves to get into with the OMR compiler technology, way back when it was first created. One of the reasons why I did the dynamic type and dynamic operation work was to try to facilitate the writing of tests in a more sort of easy to control way with this code base. And so I do think I want to spend some time thinking about how to better test both what's there already, as well as, sort of thinking about how we continue to grow the testability of the code going forward so that we can keep a better eye on correctness throughout this whole, in this part of the code.
Any questions from Mark on the design or how it works or anything like that?
Super. So, hi Mark, very interesting talk, very enjoyable talk. So one of the things that will be definitely helpful is the debugger. I think we have been sort of talking about that in our internal meetings,
Right.
especially for students. This will be very beneficial. And you mentioned, my question is, I guess, regarding reference to MLIR that you mentioned. So you also, in our private discussions, you also mentioned that some future emphasis will be sort of looking at data intensive computing. For instance, like MLIR can do data flow graphs and also various loop optimization. Do you have, or like polyhedral primitives and so on? So do you have any thoughts like in future, maybe 2.5?
Well, no, I think that's part of expanding the API going forward. I mean, I think I have ideas for creating a data flow engine. That's actually one of the very, in addition to testability, there are lots of things I'd like to do next. But in addition to testability, one of the things that I think is important to create as a data flow engine for the JitBuilder IL, it has some interesting characteristics that, well, I think have some interesting opportunities and also interesting challenges in trying to do data flow efficiently across a function builder in JitBuilder. But one of the main reasons to do that is to implement a reaching definitions, a reaching definitions analysis that can be used to further enhance the correctness checking for when you're producing JitBuilder IL, and making sure that when you produce a value and when you consume a value, that there's definitely a flow edge between all the consumptions of a value and at least some definition of that. Well, there can only be one definition of a value, but we can do that for local variables as well, making sure that values are available when you're using them. Right now, JitBuilder doesn't provide any kind of help in that regard. And it's a relatively well understood problem, so I think we should be able to do that reasonably quickly.
Thanks.
But it has like it's a usability improvement rather than sort of a performance improvement. And I think once you've implemented a data flow engine, then that opens the doors to start implementing all kinds of different analyses using that engine. And what I'd really like to push on is trying to find ways to raise the level of the API that you have to use to work with the data flow engine and to work with compiler analyses, so that you can write analyses and optimizations and transformations that where you get as much of the kind of mechanics of things out of the way as possible, and be able to focus on what is the problem that you're trying to solve in writing this analysis or in writing this optimization or in doing this transformation. It's very much early days in terms of that kind of a thing, but I think that's a theme that I think is important from JitBuilder's origins. The idea has always been to try and make it easier for people to do these kinds of things, and I think one of the ways to do that is to raise the level of interaction with it so that you don't have to pay attention to quite as many details. Pay attention to the details that you need to pay attention to, and hopefully have the system do a good enough job with the details that you don't need to, that aren't sort of germane to the problem you're trying to solve.
Yes, I agree. Raising the level of abstraction for this kind of problems would be useful.
Yes, right. So I think so. I mean, actually, just since Supra, you're the one that asked the question or got me talking. So the notion of trying to express SQL queries is one of the things that got me thinking down this line of extensible types and extensible operations, and being able to have the debugger just naturally work with those things without having to really, implement a whole raft of new code just to be able to debug it.
Right. And not just SQL queries. I mean, I think we are also collaborating with the DB2 group. So some discussion I had with them is they are mixing SQL queries with machine learning in the form of user-defined function.
Yeah.
So you now have imperative and declarative data flow code,
Right.
and
Right.
compilers can play very important.
Yeah. Yeah, being able to reuse analyses in that kind of way would be, I mean, that's kind of a dream goal. I don't have any concrete ideas on that, but it's certainly I think it's an interesting area to explore.
Any other questions for Mark? Okay.
As I
If
say,
not,
there's a pull request that's been open. It's a fairly recent one. I'm trying to remember what the number is, but I don't have it off the top of my head.
Oh, sorry, I was muted. I had a question.
Oh, yeah, go ahead.
Sorry. So this is Scott from the UMB team working on the MicroJIT project.
Yep.
And one of the objectives of the MicroJIT project initially that we kind of still have on the roadmap was the idea of a MicroJIT in OMR. One of the concepts that was very difficult to reason about in the early stages of how we would do that is how we would make a general JIT compiler that someone else would write kind of the front end to that doesn't use an IL. And the idea was floated of using kind of function calls as the IL. Build me something that adds 2 integers. Build me something that does this. And you kind of have that same mechanism in your builders for JitBuilder.
Yep.
I was wondering if you could speak about how someone might take JitBuilder and then augment it to have more than one code generator, and maybe get kind of like 2 compilers for one out of the same JitBuilder.
Yeah, so I mean, basically, there's a there's a class in JitBuilder too called Code Generator that should really be called JitBuilder Code Generator, but I got a little bit tired of saying JitBuilder all the time. I guess it could be JB Code Generator, but I mean, essentially, it's a class that visits over the IL of the function builder, and as it visits each operation, it makes calls into JitBuilder, the JitBuilder one calls, the API calls, right? And like I said, you could write a different code generator that would directly generate IL from for the OMR compiler. You could, in principle, you could write a code generator that would generate LLVM-IR. You could generate a code generator that would generate Java bytecodes in principle, right? It's all it is just as long as you can imagine the transformation framework, like what kind of runtime support you need and what kind of and what you would need to translate each JitBuilder IL call into, you can generate whatever you want. You could generate even C code if you wanted to.
All right,
So
thank you very much.
that sounds like a pretty good fit to me. Actually, we should probably talk about that.
Yeah, it may be specifically the work of what Harpreet will be working on in the future, but yeah, I would love to arrange for that kind of a talk.
Yep. And the advantage of that is that you could even, if you wanted to, you could selectively add, even optimization passes into JitBuilder too, if you want a micro-JIT that's like a bare bones micro-JIT, you could just do that. If you want to be more elaborate, you could do more elaborate things. Yeah.
Awesome. Thank you very much.
Sure. So the pull request is 6125, if anyone's interested. It's the JitBuilder 2 initial commit, it's called. Of course, there's about 8 commits inside it, but I had to make a few small changes inside JitBuilder itself too, in order to support JitBuilder 2 and some of the, in particular, the debugger, like the creation, excuse me, the dynamic type that the debugger creates required a few changes in the way that structs are defined in JitBuilder. I don't think I changed anything fundamentally, but I kind of loosened some of the rules for being able to define structs that have kind of union fields in them. And I think the kind of thing that the debugger does there is actually something that another piece of code, the interpreter builder stuff that Charlie Gracie and Igor and others worked on, and those that kind of stuff can also be implemented in a similar kind of way. So I think things like interpreter builder and sort of constructing your own interpreter and JIT using JitBuilder 2 for another language, I think is going to be a lot easier given what's in JitBuilder 2 than it has been in the sort of previous version of the API.
Okay, well, if there's no other questions for Mark, let's pause here in case there are.
Hi, it's Georgi, and I just have a last-minute question. And thanks, Mark, by the way, for showing this work, because I actually needed LLGB before I knew that, not LLGB, the debugger, before you introduced it.
Yeah.
So I didn't know I needed, but it turns out I did. So I wanted to ask rather like your vision question about whether JitBuilder will support, like, is philosophically against, or it is in plans to support persistence, like AOT style. I'm working on AOT, but I just wonder if currently we are in our home runtimes, we're accessing it by extending JitBuilder API, but the code, the discussion was started like some time ago, but it was paused for some, we decided to focus, but on persistence. Is JitBuilder planned to support persistence or not quite?
Well, I don't know if planned is quite the right word, but it's certainly, I mean, not there's no philosophical objection to it at all. I mean, I've actually kind of argued with myself over the name JitBuilder as well, just because it seems to imply that dynamic just-in-time compiler is sort of more important to it than other sort of compiler kinds of applications. And I don't think that it needs to be quite so tied to JITs, although I probably won't change the name at this point just because it's been used for so long. But I'm perfectly happy to consider extensions to the API to handle different types of code storage kinds of options. I know that I know the conversation you're talking about, and it did get kind of paused, and I know I haven't been as responsive in there as I probably should have been, but yeah, we can revisit that conversation certainly going forward.
Okay, thank you.
Yep. That actually has some connections too to the to the work that Suprio is doing too around the the questions around stored procedures and what we would do for stored procedures and whatnot, which is a sort of a more persistent style kind of code generation scenario.
Thanks again.
Sure. Thanks, Jörg. All right, well, if there's no other questions, I guess thanks to everyone for listening to me drone on. I apologize for the failed second demo. I swear that was working last night or the night before, but anyway. It's the way of the demo gods, I guess.
Thanks, Mark. Yeah, don't worry about it. This is how demo works. That presentation.
Okay,
Again,
thank you. Yeah, thank you, Mark. So I guess if there's no other questions, we'll conclude today's call, and we'll meet again in 2 weeks. Thanks, everyone. Thanks, Mark.
Thank you.
Bye.
Bye.